And yeah, so it's a beautiful sunny day, and they just announced the results of the election, so I'm super happy. So yeah,
Good
great to be
morning.
here.
Good
Hi.
morning, Chris. Yeah, sorry for interrupting. You can start your talk now, so please, the mic is yours.
Okay, great. Yeah. So yeah, welcome to my talk on architecting for rapid, frequent, reliable, and sustainable software delivery. So in the talk, I'm going to explain why that's important. I'm going to explain what it means. I'm also going to explain what it means for us as software architects. Do we architect differently? Then I'm going to talk about the role that microservices, or specifically the microservice architecture, plays and why it makes sense to use it sometimes. So before I talk about that, a little bit about me. I've been developing software for a long time. First job was like back in the mid 80s, building Lisp systems. Then over the years, did figured out, ended up in Java, wrote the book Pojos in Action, created the original Cloud Foundry, which then got acquired by SpringSource. That's where the name of the current Cloud Foundry comes from. And then for the past 7 years, I've been pretty much focused on the microservice architecture, working with organizations around the world through consulting and training, to help them adopt microservices. I wrote the book Microservices Patterns. I have a startup called DevoxxUA, and also doing training and so on online in the age of COVID. And yeah, if you want to get discounts to either my book or my online training classes, please use these coupons, and you can go to adoptmicroservices.io. So, that's me. I basically spend my time doing microservices. So talk agenda is as follows. I'm going to begin by dissecting the phrase architecting for rapid, frequent, reliable, and sustainable delivery of software. Going to break that down, explain what it means, explain why it's important, and explain its impact on architecture. Then I'm going to look at two different architectural styles, namely the monolithic architecture, and why that is a perfectly good choice for many applications. Then I'm going to talk about the microservice architecture and explain why that's a good choice for some applications, not a good choice for others. And then I'm going to finish up by talking about a key microservice architecture topic, loose coupling. And as you're going to see, the concept of loose coupling is kind of plays a major role throughout this talk. So let's get going. So I'm going to first talk about this word architecting. So obviously that's about software architecture. And then, well, what is that? Well, this is kind of my favorite classic definition of architecture. It's a set of structures that you need to reason about a system. And it consists of software elements, right? The relationships between those software elements, and then the properties of those elements and the properties of those relations or relationships, which is a pretty abstract kind of description, right? And you could sort of boil it down into architecture as really three things, right? Elements, relations between them, and properties, which ultimately is a bunch of boxes and lines, but there's sort of key concepts there. And one really important idea about architecture is that it's multidimensional. So if you think about a building, right, it could be, say, a house or a high-rise building, there's actually many different facets to the architecture. So there's the structural aspects. If it's a high-rise, that's the concrete and steel. So there's a whole group of engineers who look at it from that perspective. But then there's the electrical architecture, the plumbing, the mechanical, so on and so forth. So there's actually all these different perspectives that you can have on architecture. And each one of those perspectives is kind of a view, which itself is really a collection of elements, relations, and properties. And what those specific elements are and the specific relations depends very much on your perspective. So let's make this concrete. So, let's say we're all Java developers, right? So what does that mean? So it means that what we do is create Java classes, organize them into packages. And so from an architectural point of view, what matters there are the elements are the classes, the packages, the relationships are the arrangement of classes into those packages, and then also the dependencies between those packages. So that's sort of what I'm going to call the logical view of architecture. So that's good, and we can focus on that, and it's quite important. But then there's the deployment view of architecture, which actually is all concerned with taking our classes and packages and turning them into code, into something that is running in production. And there's a couple of concepts there. You have modules, which in Java would be jar files. And then there are components, which are a collection of modules that are executable, deployable units. And so there's this issue, it's like, what is the nature of that architecture, the deployment architecture, which actually includes the deployment pipeline, the automated process that takes our code, builds it, tests it, and then finally deploys it into production. And when we talk about monolithic architectures and microservice architectures, we're really looking at mostly the deployment side of it, which actually leaks back into how we do development. But that's sort of kind of a quick introduction to the sort of concepts of software architecture and how there are multiple perspectives or views on the architecture of the system. So why does this architecture thing matters? Well, if you break down the requirements for an application, it's basically two categories. There are the functional requirements, the stories, the use cases, which, that's all sorts of business logic, right? And then there are the non-functional requirements or ilities or quality attributes, which are things like scalability, security, reliability. And then, some of those are sort of kind of runtime things, but then there's kind of development time things like maintainability, testability, and deployability. And it turns out that you can basically implement a given set of functional requirements with almost any architecture. I mean, that's not entirely true, but it's like to just implement some business logic. Doesn't matter what architecture you have, but architecture directly the architecture of the system determines how well it actually meets its quality attributes. It determines how scalable it is, how reliable it is, and so on. So, so architecture is how we achieve the necessary quality attributes. So that comes back to the word architecting, right? Which is the process of defining the application's architecture in order to satisfy those desired quality attributes. And that's obviously something we do at the beginning of an application's lifetime. But it turns out that, over time, the ilities of the application, those non-functional requirements change, right? You might go from just having a few users to, say, in the case of Facebook, having 1 billion users. The application and the team that's developing it typically grows over time. So all sort of the non-functional attributes of the application evolve, change, and you actually have to occasionally re-architect. You can actually outgrow your existing architecture, and you have to adapt a new one. So, who is doing this? Well, that's the job of the architect, right? Which is like a coveted job description. And so if you're an architect, your job is to define an architecture that meets the required quality attributes. But what I find with a lot of organizations is that the business only cares about the user visible feature or the user visible aspects of the software, features, and then some user visible quality attributes like scalability, performance, and reliability. There's a whole set of of quality attributes that are often ignored, particularly ones that impact development, which is really the context of this talk. And architects often don't actually spend too much time doing architecture. They're typically designing big new features. And so what that means is that the quality attributes that aren't visible to the customer are usually selected. And that's where organizations get into trouble. And let's kind of look at some of those sort of more development time quality attributes. So the next thing I want to talk about is what is really meant by rapid, frequent, and reliable software delivery. Why is this relevant? And what does that actually mean for the quality attributes of the application? So back in 2011, Mark Andreessen coined the phrase "software is eating the world." What that actually means, what he meant by that is increasingly products and services are powered by software. So it doesn't matter what business you're in, software is playing an increasingly important role. Whether that's, and it doesn't, obviously banking, which is a very sort of, that's very tech oriented to begin with. But even in businesses that are very much in the physical world, like let's just say an airline, right, or a mining company, software is increasingly important to the business. So that's one key thing. It's a key trend is software is becoming really important. And also, the world in which we operate, we live, and more specifically, the marketplaces within which businesses operate are just sort of increasingly unpredictable. There's this phrase, volatile, uncertain, complex, and ambiguous. And, and a sort of more, common example of that is competitors coming out of nowhere. Deregulation of banking allows for, banks that results in banks that are hundreds of years old facing tech startups that are 2 years old, and that they risk losing market share, for example. And then COVID, who would have known, thought if you go back a year, who would have thought that we would have spent a big chunk of 2020 sheltered away and afraid for our lives most of the time, right? That's almost been the ultimate disruptor. If you look at, say, online grocery deliveries in the US, they've jumped forward 5 years as a result of COVID. So, it's just, who knows what's going to happen, which is kind of exciting and scary all at the same time. But, what does that mean? Well, it means that businesses must be nimble, agile, and be able to innovate faster, right? You can imagine COVID comes along, online grocery delivery, and suddenly the demand jumps forward 5 years in a matter of weeks, and businesses have to be able to quickly respond to those kinds of changes. And that's actually happened, I think, across multiple industries. Sort of online has suddenly taken a much more important role. And guess what? Well, that means for us in IT, we need to be able to deliver software much more rapidly, frequently, and reliably, so that we can, so that our businesses can compete much more effectively. So a good definition, a good sort of quantification of rapid, frequent, and reliable software delivery is captured by these 4 metrics, which come from this most excellent must-read book called Accelerate. And there's 2 metrics that are concerned with the velocity. Those are lead time. That's the time from a developer committing a change, doing a git commit and a git push, to that change being deployed into production. You want that's a key development metric, and you want that to be as short as possible. There's also the deployment frequency. How many deploys into production are you doing per day? So those are measuring your velocity. Then there's also some reliability metrics as well. So first one is change failure rate. What percentage of deployments cause an outage? Obviously, that needs to be really low. And then if there is some kind of outage, how quickly can you recover from it? And once again, that you should be able to recover extremely quickly. So, the Accelerate authors do this DevOps survey, and they find that high-performing organizations, developing software at a much faster rate, but at the same time doing it much more reliably. So they're pushing changes into production many times a day, and then the lead time is under an hour. And there's a crazy statistic about Amazon.com, who I think are doing at one point were doing 130,000 deploys per day, which was like one deploy every 0.6 seconds. So you have massive organization, but a good goal would be each developer commits every day, and that change gets pushed into production. And then these organizations are doing it in a much more reliable way as well. So it's sort of counterintuitive. You think, oh my God, this must be reliable, so we must do it really carefully and slowly and infrequently. And it turns out that it's backwards. If you want to deliver software reliably, then you should be just delivering a constant stream of small incremental updates to your production environment. And of course, it's flowing through an automated deployment pipeline that thoroughly tests it. But that's how you achieve success. And there's a strong correlation between how well you can deliver software and the performance of your business, which is another key finding by the authors of Accelerate. So how do we do this? Well, you have to use what I call the success triangle. In other words, it's a combination of three things. You need to have the right process, which is really DevOps, which embraces continuous delivery and development. And that's really defined by the DevOps handbook. Right? It's a set of principles and practices for delivering software rapidly, frequently, and reliably. You also need to have the right organizational structure, which is a network of small, as in let's just say 5 to 9 people, cross-functional, loosely coupled teams that are empowered to basically take requirements, possibly seek out requirements, and turn them into deployed code, or code that is running in production. So you need the right process, the right organization, and then you need the architecture that supports both of those things, that enables DevOps and enables the teams to be loosely coupled. So the Accelerate book had some super interesting findings about what it's sort of like to work in a high-performing organization. So, one point is that team members can complete their work without having to constantly meet with people from other teams. Interestingly, I've been to so many companies around the world, and one constant is there is never enough meeting rooms. And I would argue that that's probably because the way they're organized is that they're constantly having to coordinate and with one another, and it's very inefficient. But in high-performing organizations, it's almost like your daily stand-up and just informal conversations with your team members is sort of the primary communication mechanism. Another key finding is they can make large-scale changes to the design of the system without making other teams do a bunch of work for them, or without forcing other teams to do a bunch of work. Then the third point is they can do testing locally. So you sit on your laptop and you make changes and you test it, and at that point you can be confident that it's ready to go. Obviously it goes through a deployment pipeline, but you can test effectively locally. And then finally they find that you can deploy the application, a team can deploy their service without having to coordinate that deployment with other teams. So very different from sort of standard organizations. But this actually has implications for architecture. It actually means that you have to have a loosely coupled architecture. If you want to have a loosely coupled organization, you have to have according to Conway's law, you need a loosely coupled architecture. The fact that you can make changes without impacting other people that actually implies that you have a modular architecture. The fact that you can test locally implies that you have a testable architecture. And then the fact that you can deploy independently implies that you've got this architecture that are called deployable. So, once again, here's some key requirements that the architecture needs to satisfy. So that's for rapid, frequent, reliable delivery. Now let's look at what I mean by sustainable delivery, why that's important and what that implies for the architecture as well. So, if you're successful, applications, and a successful application will live for decades, 10, 20 years even. But at the same time, the technology that you use to develop software changes, right? Technologies come and go, or even versions of technologies come and go, right? At any point in time, you look in the marketplace, there's a set of technologies that are important, and that slowly changes over time. Java, 25 years old, right? So it's still important. That's a good thing. But which version of Java is important has changed throughout those years, right? And from a technology management point of view, you want to ensure that the importance of a technology inside your organization, the level of reliance that you have on it, is aligned with the importance of the technology in the marketplace, right? In other words, if you're relying on a technology that is no longer important, out of date, obsolete, you have a problem that represents some kind of technical debt. And so what that means is for these long-lived applications, we need to be able to incrementally upgrade the technology stack. Obviously, you can always do a complete rewrite, but those are actually incredibly expensive and risky. So you want to be able to incrementally switch out the technology that you're using in your application in order for it to have a long, healthy, sustainable life. And this is actually another form of modularity, right? Where, in a sense, normally we think about modularity as where the API encapsulates various design decisions. Well, here I'm sort of expanding that definition of modularity to include the API in encapsulating the technology choices that you've made in your application. And you could imagine that there's very few ways to achieve that. One obvious way, of course, is you hide something behind a REST API, right? And then doesn't matter what's behind it. And that kind of, to me, is like, this is hinting at the importance of the microservice architecture. But I'll get to that in a minute. So put all of this together, right? You need an architecture that's loosely coupled and modular, both in the regular way and also sort of in this way that encapsulates technology. And you could also call that evolvability or evolvable as well. Plus, there's a requirement around testability and deployability as well. So that's the architecture that we need for rapid, frequent, reliable delivery of software. So let's look at a couple of choices, right? If you were to go on Twitter today and say, ask a question, what architecture should I have for my application? You'd get answers like the monolith, microservices are a total mistake. And then there are other people that are going, well, microservices are the way to go. It's the future, right? And so, there's been some great tweets about, very polarized discussions and some great tweets either way about that. But as you could imagine, I mean, from my perspective, the answer is very much, it depends. Depends very much, what on sort of fundamentally the size of your application. So let's look at the monolithic architecture, right? So that's an architectural style that structures an application as a single executable or deployable component, which in other words, what's getting deployed into production is either in a Java sense, a WAR file, or it's an executable jar, right? I mean, those are the common ones. And you can imagine at the start of the application, you just, make a directory, CD into it, and then you start typing away, right? And literally, I've worked at startups where pretty much that's how development began, right? So, an example application would sort of look like this, right? Bunch of very sort of modular packages and that get turned into modules, modular layered architecture. That all gets packaged up into a WAR file or an executable jar or something, and then it's talking to the database. So, and then there's a browser. The application's either generating HTML or it has a REST API or something like that, right? So anyway, that's sort of a typical monolithic architecture. And this is a perfectly good choice for a lot of applications, right? Because if you have, especially when they are small, because a small application is highly testable. You can test it locally on your laptop. The amount of time it takes to test is relatively short, right? Deploying means just pushing it into production. That's pretty straightforward. It tends to be easy to maintain, right? The code base is kind of small. And then if you design your package structure correctly, it's modular. And it's kind of sort of evolvable in the sense that, well, yeah, you can swap out the technology stack by doing a complete rewrite. But if the application is small, that's not impossible. But the problem that you have is, that's tiny application that maybe it had started off in life as a single, one directory. You just started with make dir, and you've got half a dozen developers. If you're successful, you're likely to end up over time with a large application, right? Many millions of lines of code. I've worked with clients that have had applications where the WAR file itself is measured in gigabytes, right? And then the number of developers you have working on it is measured in the hundreds or thousands. That's the sign of success. But once you get into, once your application reaches that scale, you have a whole bunch of issues, right? Even just committing changes into a single source code repository when you have a lot of developers is problematic, right? There's a contention for actually doing commits. Obviously you can no longer do teams can't deploy their work independently. Because everything is packaged together with every other team's module, and they all have to deploy together. If you've got a very large application, in order to reduce the execution time of the deployment pipeline, it needs to be parallelized. It needs to be running on a cluster of machines. So you've got this complex infrastructure for doing builds. And then ultimately, you run the risk that the actual act of updating production, which ends up, I feel like, can't really be parallelized, ends up being a bottleneck. So the rate of change, I think, ultimately will kind of just bottleneck at some point. Now, you could have a more complex architecture where you split it up into, each team has their own repository, and that actually parallelizes the build, and each build pipeline spits out a compiled module that then feeds into the application level deployment pipeline, but you still risk having a bottleneck there. So there's sort of some inherent issues around scalability at this point, sort of from a development perspective at this point. So you sort of end up with this graph where over time the size and the complexity of your application grows, but then sort of the kind of the desirable development time soft quality attributes gets worse and worse over time, right? Testing is likely to take longer, deployment takes longer, so the sort of the rate of change kind of just plateaus. And this is a problem for the business, right? Because you really need to be going faster and faster, and there's a real risk of disruption as well. So you can kind of mitigate some of the problems of having a large monolith by throwing a bunch of technology off at it, but ultimately, I think it's quite difficult to do at large scale. Plus, there's this huge problem where many of the technology choices in your application are global, right? It's basically, ultimately, you've got, say, a giant executable jar file. Well, you have committed to using the same version of Java. Well, first off, you're committed to using Java. You're committed to using the same version of Java. And unless you start getting into the complexities of the Java module system, for the most part, you can only use a single version of any given library, third-party library. And so that actually makes it extremely difficult to make changes, to sort of to change your technology stack. And you basically end up being locked into the original technology choices that you made. And I think there's a lot of organizations who are sort of stuck in this situation. So, you end up in what I call monolithic hell. I mean, it's not inevitable, but there's a very high risk of that. So what can you do about it? Well, of course, obviously, the alternative architecture is the microservice architecture. So that's an architectural style that basically structures an application as a collection of services or components, right? So instead of effectively a single executable, a single deployable, you have many of them or multiple executables and deployables. And each one of them is highly maintainable, testable, has a minimal lead time. Each one is independently deployable by definition. And they're obviously loose, that they need to be loosely coupled. And then the last point is super important. Each service is owned by a small team. So if we were to look at the food to go application, it would consist of multiple services. Each one of them has its own database. They're communicating via a message broker. You can sort of functionally break up the web application into multiple web apps as well, each one implementing a particular part of the UI. You'd have an API gateway in front of it, exposing APIs to the outside world, right? So, instead of one thing, this architecture is broken down into a bunch of services, which actually hints at the complexity, right? Like there's a bunch, in the deployment perspective, there's many more moving parts, many more boxes and lines. So, what is a service? The whole point of a service is to expose an API. In a sense, the whole purpose of a team is basically to expose an API. The API implements operations, right? Things that clients can invoke. There's two types of operations: commands that mutate data, create order, cancel order. There's queries that retrieve data, like find order history. And these operations can be invoked either synchronously, which is sort of how we normally expect it, but importantly, they can be invoked asynchronously as well. Services also expose events, typically like order created, order canceled. So when key changes occur in the service, it's common for it to publish events. And then services can invoke operations implemented by other services and consume events emitted by other services. And the service also has its own database as well. And I'll talk about that in a little while. But the idea, though, is that the service database is an implementation detail of the service. Services typically implement business concepts. So a service implements a subdomain, or if you're familiar with DDD, or it would implement a business capability, which is a term from business architecture. So there would be order management, delivery management, accounting, so on and so forth. And another key issue is sort of like what's the granularity of services, and what's the size of a service as well. So given that the primary goal is to enable a team to be autonomous, so needs to be a loosely coupled architecture to support loosely coupled teams. Ideally, you just want to have one service per team, as few as possible. And also, given that the team is should be small, 5 to 9 people is a good size. That actually imposes an upper bound on the size of the size and complexity of the service as well. So that's sort of a rough sense. And interestingly, a bunch of organizations I visited, they actually tend to have like a service per developer, which arguably is far too fine-grained. It's just too much complexity for insufficient benefit. Having said that, it can be useful, it can be useful to split a service if it solves a tangible problem, right? So imagine, over time, the service grows and the team grows. Well, that would be a reason to split the service and split the team to keep the team the right size. If the deployment pipeline takes too long, well, you could split the service into 2 that can be developed and tested independently. Obviously, there's very little, not so much benefit in splitting a service into 2, which then constantly are having to change in lockstep, right? That's a sign of tight coupling between those services. You might need to split to support polyglot development. So imagine your data analytics team has produced a fraud detection algorithm in Python and machine learning model, right? But the rest of you're using Java. That would be a reason to have a Python service. You might want to split for fault tolerance, like high parts of the application that need to be highly available, like the critical path for processing credit card authorizations might be separated from merchant account management, for example. So if I'm working on merchant account management, well, I don't want to impact the credit card authorization logic. You might also want to split for regulatory requirements as well, where if you have part of your application is subject to strict regulatory requirements like PCI or some sort of health care related requirements, well, you could split those off so that the development of the rest of the application is not impacted by those fairly burdensome regulations. So a whole bunch of kind of issues that can drive introducing more services, but you should only have services should exist for a good reason, not just because. So the bunch of benefits to this, right? It improves maintainability. I think each service is small and fits in the head of the developers who are working on it, unlike a massive monolith, right? Each service is small and easier to test and faster to test, so it improves testability. You can change each service's technology stack independently, and I'll talk about that in a minute. Each service, by definition, can be deployed independently, which means the teams don't have to coordinate. It can improve scaling as well, and it can improve availability and fault tolerance as well. If there's a failure in one service, it doesn't necessarily impact other services. But by far, the biggest benefit of the microservice architecture is that it enables DevOps. It provides the testability and deployability that DevOps needs, and it provides the loose coupling that's vital to enable the teams to be loosely coupled as well. So you end up with a situation like this, where each team is committing changes to their services code repository. There's an automated deployment type pipeline that's building and testing the service, and they're all working independently most of the time, unless they have to coordinate their work to agree on API definitions. But most of the time, these teams are working independently. And then I think a huge benefit, which is important for these long-lived applications, is that you can experiment safely with new technologies and incrementally evolve the technology stack, right? So imagine that you get all excited about Golang, right? You could go implement a service in Golang, even though the rest of your services are implemented in Java. You can safely experiment with that. But then, and if you like it, that's great, that experiment has succeeded, and you've now figured out that there's a new technology that you wish to incorporate into your architecture. But on the other hand, you want to use, say, a more 21st century language. You might decide, well, yeah, we want to use Kotlin instead of Golang, right? And that's okay. You haven't invested much time in experimenting with Golang. And at some point, you could, when you're going to make major changes to that service, you could rewrite it completely in Kotlin, for example. So it lets you experiment and incrementally evolve your technology stack. And obviously, these services, even the Java-based services, they don't have to use the same version of Java, right? Each one can evolve at its own pace. They don't have to use the same versions of third-party libraries. So you avoid all of the issues that you can get into with a monolith, which basically requires you to use a single technology stack that cannot be evolved incrementally. But there are some significant drawbacks of this architecture. You're building a distributed system, so you've got all the complexity of distributed system development, inter-process communication, for example, right? Complexity around testing. On the one hand, testing individual services is easier, but testing that they work together involves adopting some new techniques like consumer-driven contract testing. And then from a deployment perspective, there's many more moving parts in production that need to be orchestrated and monitored and managed and so on. So it's sort of like kind of the sort of like, for small applications, you should stick with a monolith. But once your application grows, the benefits start to outweigh this complexity. And then, there are some issues as well, like correctly identifying service boundaries. I mean, that's an interesting challenge. There's no mechanical process for that. Yet at the same time, figuring out what your service boundaries are is the most important decision that you can make. Choices around technology are very secondary. And then if you have a monolith, refactoring that into a microservice architecture can be painful and time consuming. So it's sort of, they're not easy to adopt. But on the other hand, if you've got a massive monolith, you're most likely in a world of pain anyway, and you have to embark on this refactoring effort. So it sort of boils down to, if you're developing a large, complex application and you need to deliver it rapidly, frequently, reliably, and sustainably, the microservice architecture is a good choice. But if not all of these things are true, then probably the monolithic architecture is a better choice. Okay, so I want to finish up by, that's sort of a discussion of the two architectural patterns and why they're relevant and when you should choose one over the other. I want to finish up by talking about the architecting loosely coupled services, because this is a key sort of requirement that often people get wrong. In fact, I mean, there's one blog post or one company, they built a tightly coupled set of services, and it was even worse than having a monolith. and they actually had to rewrite it back into a monolith, though they did get a conference talk out of it. So, but they sort of fundamentally they ignored this point. So this all goes back to Conway's law, which is fantastic, right? I've been hearing of Conway's law for decades, and it turns out that he's on Twitter, which is so awesome. So basically what he said, paraphrasing, is that the organizational structure, or specifically the communication patterns in the organizational structure, who talks to who or who reports to who, mirrors the software architecture, and what that and vice versa. And what that actually means, that if you want to have loosely coupled teams, you got to have a loosely coupled architecture. And there's actually, which is interesting, right? So services almost often have to collaborate. So in my example, when in order to verify that an order can be created, the order service has to reserve credit, which requires checking with the customer service. So collaboration is, inevitable, which introduces a certain amount of coupling, but you want to do it in a way such that they are loosely coupled. Turns out that there's two types of coupling, at least two types. One is runtime coupling, which is where one service cannot respond to a request until the other service responds to it. And I'll talk about that in a minute. And then there's design time coupling, which is where at development time, when you change one service, you kind of have to change another service in lockstep. And a key thing to remember is, just because you have microservices, you are not guaranteed to have a loosely coupled architecture. You have independent deployment, which sort of feels like loose coupling, but you have to design your services to be loosely coupled. And loose and tight coupling is a problem because it requires coordination between the teams, meetings to discuss API changes, which slows down development. People at ThoughtWorks have found that decision-making across teams is 10 times slower than decision-making within teams, and it can slow down development. In the worst case, you can end up with what's known as a distributed monolith, which is where multiple services are frequently changing in lockstep. So it's really important to prevent tight design time coupling. So there's a few things that you can do. So one is, this is an old concept of you apply the dry principle. Don't repeat yourself. So in other words, every concept should be represented in one place, and you translate that into the microservice. Every concept should be represented in just one service. If you have the implementation of a concept scattered across multiple services, whenever that concept, think business rule, changes, then all of those services have to change in lockstep. So that is a bad thing. A change should ideally only impact one service. You also want to design your services to look like icebergs. The saying goes that the visible part of an iceberg above the water is much smaller than what lies below. So you want to have services with relatively small APIs that are stable, that can encapsulate a much larger implementation, because what's hidden can be changed, right? And what's exposed in the API is much harder to change, because you're, if an API, worst case, if an API changes incompatibly, then that requires all of the clients of that API to be updated, which is, painful. So you want to design services with thin APIs that hide a lot of complexity. Great example of that is, say, like Twilio messaging, right? Like you want to send an SMS. It's like, well, it's roughly send message this from this number to this number, and here's the message, right? Incredibly simple API that encapsulates a massive amount of complexity. So it's a key principle. You want to avoid having putting business logic in shared libraries, because whenever that business logic changes, all of the services that use that library have to be updated, requires them to change in lockstep. Now, if you do this, this could lead to a conference talk, as did the company I mentioned, but it's best avoided. Now, you also want to avoid sharing of database tables. Database schemas are implementation details, right? And so, if you give access to if you let other teams access your database, changing it is no longer straightforward. So it's best avoided. You should really encapsulate the database. So that's design time coupling, and a set of principles that can ensure that your services are loosely coupled and reduce the amount of coordination that's required amongst the teams. Now, I want to mention loose runtime coupling as well, even though that's sort of related, but it's quite different. But this is another common anti-pattern that I've seen when I've worked with various organizations. So if you think about, let's think about, well, we got a bunch of services. How are they going to communicate? And it's like, yes, well, they just use REST, right? So imagine like the order service handles a post request that creates an order by doing a put request to the customer service to reserve credit. Looks super simple, right? And then the response comes back that enables the order service to create the order, and then it sends back a response to its client. Superficially, very simple, right? It's mirroring the communication pattern inside a monolithic architecture, but you've just designed a system where the availability of the create order operation depends on both of those services being available at the same time, right? Both being up and both being able to respond have a response time that's within their SLA. And so its availability is really the product of the availability of those two services. Now, in this simple case, maybe it can work. I mean, there's some actually other interesting design issues that you get into, but you've reduced the availability of your system. So it's sort of like this distribution is free anti-pattern. And I remember one time I visited a client. They had this critical API endpoint that was integrating with a third party, and there was really strict SLA requirements, right? Like around availability and around response time. And by the time I talked with all of the teams that were involved in implementing the services that were invoked, became apparent that like 10 plus services were being invoked, which, so they were risking, not meeting their SLA because if any one of those services was down, right, they couldn't respond. Or if any one of those services was exhibiting extremely high latency, they could not respond either. So it represented a major risk to the business. So you should be very wary of long chains of synchronous communication. So there's a really key concept, which is this idea of a self-contained service, which is a service that can handle a request without waiting for a response from another service, right? So the order customer example I had earlier, the order service was not self-contained, right? Because it had to interact with the customer service. So so it didn't fit this pattern. So one way of making it fit this pattern is to actually merge together the order and order service and customer services, right? That improves the availability of this critical operation, right? So that's good. But at the downside is that the team is much larger. Now, depends on the situation, this might be a worthwhile trade-off, or it might not. So, once again, it depends, right? But quite often, you can't, if you followed that path, you'd basically end up with a monolith. And we've agreed that in this situation, we want to use services, right? So you can adjust service boundaries, but ultimately you might have to have some kind of communication. And for there, it's actually best to have asynchronous communication. I highly recommend this book, Enterprise Integration Patterns. It's a great pattern language. So one way of implementing the order service using asynchronous communication that gives you high availability is as follows. So the post order request kind of basically initiates the process of creating an order, and the order service responds immediately. And in the meantime, a bunch of events are exchanged. So the order service says, I've created this order. That event gets consumed by the customer service, which reserves credit, sends back an event to the order service, which can then change the status of the order to rejected or approved. And this specifically is a choreography-based saga. This is more available, right? The order service can respond to a create request without waiting for any other services. But you've got the downside is you've got the complexity of sagas. And another interesting thing is that it changes the meaning of the API. The response that comes back first cannot say whether the order was accepted or rejected based on whether there's credit available or not. So the client has to check back later to see whether its order has been approved or not, or maybe it could consume events somehow. So there's some super interesting trade-offs with this, right? But this is a very useful pattern to use. The other pattern that you could use, which I call, is command query responsibility segregation, which is basically a complicated way of saying, well, we're going to replicate data to the order service. Specifically, what happens in this design is the credit limit is replicated to the order service, and the order service is made responsible for tracking available credit. That responsibility has been taken away from the customer service. So that actually gives the order service the data that it needs in order to decide whether there's credit available. And we've made it self-contained, right? So it's more available, but the response does contain the outcome of the operation. But you've got the cost and the complexity of replicating data. So you sort of got these different sort of trade-offs, right? Between you can merge services together, right? Which means merging teams, which is problematic, but maybe a good idea sometimes. Or you keep them separate, and you either use sagas to maintain sort of data consistency across these services, or make them self-contained, or you can use replication. And each one of these approaches sort of has different trade-offs. Now, like for instance, you could replicate the credit limit to multiple services. That's okay, but only one service can be responsible for managing the available credit. So if there were multiple services that needed to maintain available credit, that would not work. You'd have to keep that back in the customer service and use sagas. So anyway, so that's sort of it. So in summary, right, couple more slides. So there's some trends that are requiring IT to deliver software rapidly, frequently, and reliably, right? The fact that software is powering businesses, and the world, the marketplaces are unpredictable. You have to embrace DevOps. You have to embrace a network of loosely coupled teams as your organizational structure. And then another key trend is that software lives for a long time. So we need to be able to upgrade the technology stack. So that then leads to you need an architecture that's loosely coupled and modular and testable and deployable. Now, so, the monolithic architecture is a good choice for small applications that are developed by a small team. But once the application becomes large and you have a large team, often the microservice architecture is a better choice. And if you adopt the microservice architecture, you need to design your services to be loosely coupled, both from a runtime and design time perspective. So that's my talk. Thank you for listening, and I hope that you found it useful.
Thank you, Chris. Thank you so much for connecting today and presenting this talk and supporting Devoxx Ukraine. Dear participants, you can ask your questions. Thank you. You can ask your questions to Chris during Q&A Zoom room just now after this talk, and you can unmute, turn on your video, and have a discussion with Chris. Yeah, so thank you once again, and we hope to welcome you in Ukraine next year.